Hi, this is Team 15. The team members are Zachary, Lugie, Swayam, Connor, and myself, Mario. This is the final presentation of our project, analysis and redesign of a Marshall MG15FX guitar amplifier.
Electric guitars are a cultural symbol that represents a variety of music genres like jazz, rock, pop, and even country. One indispensable piece of equipment to play an electric guitar is a guitar amplifier, which creates a high-power replica of the signal input from the guitar. Our DfM project focuses on this device. Our primary and secondary customers are hobbyists or first-time buyers and experienced musicians or enthusiasts. For a hobbyist-oriented design, the capabilities required are signal amplification, 3 effects channels, and a simple equalizer control. Given this customer subgroup is most likely inexperienced, the frame and body of the amplifier must be durable, comprising of rigid wood, resilient surfaces, and a sturdy handle. For a design oriented towards elite players, the capabilities required are signal amplification with manual or auto-tuner selection, 7 effects channels, and an advanced equalizer control. The construction of this design features more stylized components like a grill cloth cover, molded branding, and a comfortable rubber handle. The design is also structurally solid, with rigid wood and protective corner guards.
The main function of the Marshall amp is to amplify the signal or sound from the guitar. To do this, it must first create sound. Once the sound is created, the amp can modify the signal of the guitar to change the volume or alter the signal to make it sound different. The design must protect its users by preventing electrocution. This can be done by enclosing exposed wires and insulating exposed leads. To assure convenience, the design includes a handle to assist transport. Adding an auxiliary input and a headphone jack will enhance the product, and finally, the design must appeal to the brand by having its logo. Taking from the FAST diagram, the function component mapping matrix identifies the relationship between the functions of our product. As you can see in the diagram, a couple functions share parts, as in to change volume we have the volume knobs, the volume/effects knob PCB, or for enclosing wires we have the wood casing, back wood cover, front cover, and console casing, and etc.
Here we have a breakdown of the components that belong to the common platform as well as the components that belong to each one of the amp designs. Our optimized design uses fewer and simpler components, while maintaining functionality as required by the primary customers. The original amp design is more complex and thus more expensive, yet it satisfies the requirements of the secondary group of customers. Some core components remain a common platform between the designs. These are the amp case, the speaker, and the power transformer. The premium appearance of the secondary design results in more components and materials being necessary for its construction. Some of these components don't necessarily realize a function, but rather contribute to the visual appeal of the amp, such as the injection molded brand logo and the grill cloth. Others do realize a core function, and yet go beyond the minimum requirement to contribute to the higher quality feel of the design, such as the EPDM rubber handle. Finally, the several sound effects inevitably result in more electronic components, which in turn require a larger and more complex mounting bracket.
Now we need to analyze the manual assembly of our primary product. The handling time and insertion time of each part can be estimated by referring to 2 timetables. Adding all the time together, we calculated that the total assembly time of the primary product is around 429 seconds, with an assembly efficiency of 6.3%. Meanwhile, we can observe that the power transformer and the corner guards are the platform part and the modular part that need longest assembly time. Since the assembly efficiency is low, the primary product must be redesigned.
On the primary design, we only need to maintain the core sound functions of the amp. The electronics are then relatively simpler, and thus can be contained in a single PCB. This in turn allows for a simpler design of its mounting bracket. We cover the bracket optimization in more detail later on in this presentation. One recurrent optimization theme in our primary design has also been reducing the amount of fasteners needed, which is accomplished by redesigning some components with slight fit features on one side, as we can observe in the handle, the power transformer, and the PCB.
After redesign, we can find that the total assembly time has been reduced from 429 seconds to 221 seconds, and the assembly efficiency has increased from 6.3% to 9.5%. The redesign of the primary product helped us greatly reduce manual assembly time and facilitate subsequent automated assembly.
For automated assembly, the sub-assembly part we chose to redesign was the rubber feet. In this slide, we calculate the total handling cost and the total insertion cost of both these designs using the respective equations given below. After comparison, we saw that the handling cost for the cylindrical design proved a 15.7% reduction, where the insertion cost for the cylindrical design gave a 20.5% reduction after calculation. Listed in this slide are a few benefits of our redesign. Having the rubber feet in a cylindrical shape makes the part 180-degree alpha symmetric, whereas the trapezoidal shape had the part at 360-degree alpha symmetric. This 180-degree alpha symmetry allows the rubber feet to be fastened in any direction, compared to the trapezoidal shape, where that wasn't possible. The cylindrical shape also increases orienting efficiency, which thereby reduces the total handling costs. Overall, this design makes assembly quicker and more efficient, as orientation is no longer an issue.
The electronics bracket holds PCB and power transducer. Tolerances of plus or minus 0.15 mm are precise due to concentric fit with the potentiometers on the PCB. The fitment of the power transformer has a tolerance of plus or minus 0.25 mm because there is no critical fit. The two processes we found were machining and sheet metal forming, but given the complex shape of the clip feature, we would recommend sheet metal forming. We would recommend using a low carbon steel as a material, strong and ductile, so it would be easy to form. The support foot supports the amplifier and reduces vibrations sent to the ground, helping it stay in place. The tolerance of plus or minus 0.25 mm was chosen so the part would remain level to the ground and so the bolt would properly fit through. The two processes we found were machining and injection molding. Because each amp has 4 of these parts, the batch size is large, so we recommend using injection molding. For material, we recommend using EPDM rubber because it has good protection from the environment and vibrations.
We did a sheet metal working optimization study to reduce the manufacturing cost of the electronics mounting bracket. The 3 improvement points are eliminating the bending process, then reducing the amount of piercing holes by virtue of having simpler electronics and thus not as many control knobs, and finally, making all outer edges of the bracket straight, so we can move from part-off to cut-off separation in the sheet metal working process. We observed a sheet metal working cost reduction of 62% by implementing these improvements.
The product service systems for this amplifier caters to our primary and secondary customers respectively. Our hobbyist-oriented product service system provides a cost-effective amp rental program with hourly beginner-level lessons to help with getting started and guidance with simple effects. Our product service system for the more experienced musicians include the advanced amplifier design paired with professional venue setup.
After completing this project, we now have a clear understanding of the needs of different groups of amplifier customers. Furthermore, we know how to carry out the DfM and make components easier to build and assemble while maintaining their functionality. As for the pros and cons of our design, we are very confident about the future market performance because our product still maintains the most core functions. One drawback, however, is that in addition to different prices, it can be difficult for new customers to tell the hands-on difference from other version. We have to admit that if we can find a lighter and cheaper material to replace the pressed wood, our products will become more competitive. If we can redesign the product again, we will consider further reducing the number of fasteners. One alternative is to explore eliminating the electronics mounting bracket and having the PCB mounted directly to the case.